All right. So, today, what we're going to do is we're going to implement our own sort of transformer model. And this is actually for educational purpose. We want to dig deeper inside these transformers, and we want to understand that what's going on underneath, right? So we've actually done pretty much. We've actually covered the first part, that is basically creating your own tensor abstract. And then using that tensor to create the weight matrices for QD values and key matrices, and generating token IDs, and generating token embeddings against those token IDs as well, right? And once this is generated, we actually went ahead and we did something even cooler, which is like, implementing multi-head attention. And what it is basically, it takes the tokens and it takes the shapes of the weights, and weights are basically, you can say, QD keys and value matrices, and number of heads. And if you have any idea about how multi-head attention works, basically it just concatenates the scale dot product attention. And basically what happens is, if you have a dimension model dimension of, let's say, 512 or maybe 1024 or whatever, you just kept your embedding size. What it is basically, it just divides your heads, and each head is responsible for that very specific chunk of the final embedding that you are supposed to get, right? For example, let me just try to understand what happens basically. All right, so if I open it here, let's just delete this thing. So let's just say our model is supposed to return this thing, this huge excuse me tensor of, let's say, for the sake of simplicity, 32 length of embedding dimension. So what basically happens is, if I have, let's say, 8 heads, and if I divide 32 divided by 8, that's going to be 4. So in multi-head attention, what will happen is, uh, for to make this entire 32, we'll have 8 different heads working. Each will have their own dimension, that is called head dimension, something we represent by dk. And if you ever come across this formula of attention, that that's having q, k, and v as a function parameters, what it does basically is it applies softmax upon q times transpose of k, in order to like make the matrices ready for multiplication. You gotta have this first columns matching the rows of the second. Yeah, that's right. So we need to take the transpose, right? So divided by square root of dk, right? Dk, and multiplied by values matrix. So what this dk is basically, this dk is embedding size divided by number of heads, which in our case is 8, and that gives us 4. So basically, I'm writing it pretty bad since I don't have the pen tab. It's only the mouse that I'm using, but I'm sure you're able to grasp the idea that what happens under the hood, right? So that's how we get the head dimension, and this is what we call head dimension. This is basically a scaling factor in order for our attention mechanism to work properly and do not saturate the softmax, and do not um, explode the gradients, right? So yeah, okay. So this is our this is supposed to be our tensor that we want to get in response, and these are actually the number of heads that are actually responsible for giving us this output embedding, and each head will have its own embedding dimension, and that's in our case going to be 4. So what happens basically, think of it like it's a huge matrix that it stores each and every token's context, semantic meanings of each token, um, with respect to all the other tokens, and that's how our attention mechanism works. So what we do is we divide this entire context vector to be obtainable by each head, and then what we do is we just go ahead and row wise concatenate these, and each chunk will represent some meaning that it has learned, right? um, Using this multi-head this attention mechanism basically, and will concatenate these chunk embeddings, these chunk semantic meanings, to form one large embedding that is the entire representation of that particular token. Now you may ask the question that why we divide this into number of heads, and then why don't take it only once, like only once, like using 512 dimension length. Why we just use every single head and break this 502 into number of head dimension and then calculate and then concatenate? So the simple answer is we want to grasp as much language meanings, and we want to preserve as much language meanings as possible. So what does that mean? That one head might be responsible in learning the grammar, the other would be responsible for learning the most probable next word, the other one would be responsible for catching the long-term dependencies, for example with first word to the last word or something like this. So each head is responsible, in simple word, to grasp the idea, the core understanding of the language, the way it works, right? So each head understands different attributes of the language, and then we sum them up to form one large head that has multiple slaves or multiple sub level works which are responsible for each specific area working under that, right? So with that intuition, let's just move forward and say where we were. So basically, it's just a matter of implementation. Theory has been explained. We gave the shape dimension, shape weights, and a number of heads, and then we just go ahead and just obtain the decay, like I mentioned, and then we allocate some memory. And this is basically array pointer of our um, output heads that we later will be concatenating, right? So it's actually a pointer to the pointer that stores pointer inside it. So array pointer is storing the structure pointer um, inside it, which is a tensor, right? This is structure is basically stores the tensor pointer. So we'll have a number of heads, many tensors inside that array, right? So what we do is something that we did slightly wrong over here is we have initialized the weights inside this for loop. That's not what we should do, because each time it will generate the um, you can say random weights, right? But we need to have one set of weights and till the end, that'll be that'll be learning along the way, and then only once at the end we'll update those weights, right? So we'll fix this later. For intuition, for understanding the concept, we have done it this way, right? So what's happened is we generated these weights, QDs, values, and then we went ahead and applied a made mult operation, something we've mentioned in our tensor file, which is here. Tensor, we've actually implemented all these functions previously over here. So if I go like tensor, let me just show you matmul or matmul. Yeah, yeah, tensor matmul. So what it takes basically is it take two tensors and just multiplies them. That's it. Nothing too fancy. So this is actually the dynamic allocation of the memory of the tensors, and this loop does the job basically, right? So if you've used the strides, you can also use the index formula like I times columns plus j for row major, but we've used stride for that. We'll cover this in some other video. So for now, let's move back. All right, so this is our multi-head attention attention function, and once it obtained a scale dot product attention, something that I just explained over here with this formula. It's just implementation, nothing special. And then we just go ahead and you know append the attention squares to a defined array, which we define as a pointer to the pointers of the structures, right? And then we just went ahead, and this is supposed to be our output matrix. Since we need to concatenate them, we cannot just represent it as a pointer array, but we actually have to represent this as a tensor. So think of it as like the idea is to find the size of this um, result matrix. It's a little tricky thing over here. So what happens is basically we first define it, and we define it like in such a way that where have I defined it? I mean, where's res, where's res. Where have I initiated this res Z? Okay, yeah, there it is. And dimension is shape of R, and shape is actually the key. So if I go here and check what happens, uh, res tends to create and dimension shape of R, and shape of R0 is sequence length, and shape of R1 is embedding dimension. Yeah, yeah, that's right. So the res is nothing special. Since, like I mentioned over here, is what we have done here is we this is actually we're not actually extending the size of this output tensor. It's same as the embedding dimension as for each token, but what we're doing actually, we're making responsible each head to obtain the chunk of this thing, right? So this should not exceed from embedding dimension, right? This has its own fixed size as the embedding of one single token. The only difference is the decay does the rest, because each large context vector will be shrink down to will not be shrink down, basically will be distributed into the number of heads, and each head will be responsible to find the chunk of embedding that we will later concatenate, right? So we define this resultant vector shape, something the offset which we need to define, because for decay will be like progressing each number of head columns along the array. So we need to define some offset to skip and find the right index pointer to copy the next tensor there. So I just looped over here, extracted the first head, 0th position, extracted the rows and columns, and now I looped I traversed this head, and then I'll find the source index, and source index is going to something row times head of the columns plus column, right? And then this destination index would going to be rows times the columns of the resultant matrix that we are supposed to get in the output, and offset plus c, and this offset will be added each time to skip the dk times spaces, uh, right? So then what we need to do is we need to copy the data from source to the destination, and increment offset by head columns, because we need to skip the head columns. Let me explain it like in a bit more detail. So what happens basically is all right, so what happens basically is, this is our, let's say this is our res that we need to get, and this is our h1, this is our h2, and so on till h, let's say 8, and this will have dimension of 4, and this will have 4, and these all will have 4 dimensions, right? So what happens is basically, this is our source and this is our destination. So in order to find the index, the source is going to be like a row times head columns plus columns, and this destination is something a bit tricky. So this, for destination, we are using this thing, um, this res. So this is going to be r times rows times res columns, not head columns, res cols, plus c, and offset is added here. And this offset is basically this head, right? So each time when you traverse, or you can say like when you'll be adding the heads, copying the heads, concatenating the heads into this final matrix, what will happen is each time you will skip these many blocks. First time we'll skip this one, the offset will be added, and next time we are just incrementing this offset plus equals head columns. So each time it will have the head columns added for the next iteration, and we'll skip these many positions, and we will start copying, concatenating from this pointer index, right? So yeah, same thing we've done over here, and yeah, this is pretty much it. And now let's just run our script and see everything is working. So I've already created a run.py file. Remember, we need to compile attention plus tensor as well, because they're because I've introduced some guard headers as well, and attention is dependent on this tensor as well. So if I run this, run, you'll be able to see 10 cross 32. For now I've kept embedding dimension 32, and I've passed the sequence length of 10. And yeah, I'll see you in the next video.